Last time, we saw that every digital twin depends on a trustworthy model. Let's move one level deeper. Why are complex physical systems difficult to model? They involve many interacting processes. They involve overtime. They operate across multiple scales. Battery systems make these challenges easy to visualize. No physical process acts alone. Electrochemistry generates heat. Temperature influences reaction rates. Mechanical stress leads to cracking. Degradation alters electrochemical behavior. Each process influences the other. That's multiphysics coupling. The challenge is describing how they evolve together. So, how do we build a model for a system like this? We usually begin with physics. When the underlying mechanisms are understood, they can be described mathematically. In batteries, one widely used example is a pseudo two-dimensional model. It captures electrochemistry, transport, and material behavior. As more physical mechanisms are incorporated, the model becomes more detailed and more computationally demanding. This improves physical fidelity, but also makes real-time simulation and deployment difficult. Physics-based models remain the foundation of scientific modeling. The challenge is making them practical for real-time learning and decision-making. Another approach is to simplify the model. The goal is to retain the behavior that matters for application. This is a principle of reduced order modeling. The equivalent circuit model is a common battery example. It replaces detailed electrochemical equations with a set of electrical components. This enables fast simulation and real-time implementation. The trade-off is reduced physical fidelity, especially under conditions that differ from those used during model development. A third strategy relies on data. The model is learned from observations rather than derived from first principles. Given sufficient data, it can represent highly nonlinear system behavior with flexibility. Its behavior, however, depends on the quality and the quantity of the data. Predictions become less reliable as operating conditions move beyond observations. Physical consistency is also difficult to guarantee. No modeling strategy is universally optimal. Each reflects a different modeling philosophy. Physics emphasizes mechanisms. Reduced order models emphasizes efficiency. Data-driven models emphasize flexibility. Digital twins require all three. No single modeling strategy satisfies every requirement. Modern modeling is moving toward integration. This is the motivation behind hybrid modeling. Physics-informed learning integrates physical knowledge with data-driven learning while preserving physical consistency. It reflects a new way of thinking about complex systems. We will continue from there in the next lecture.